Welcome to Data Skeptic. Data Skeptic brings you discussions about how data is changing our world. Our interviews are conversations with thought leaders in topics like data science, machine learning, and artificial intelligence.
One note and one announcement before we get into our interview. My guest today is Pedro Domingos, author of The Master Algorithm. We're going to be giving away 2 copies of the book. Stay tuned at the end of the episode to hear the details on that. The correction, a foreshadowing correction actually. During the interview, I used the phrase fuzzies and neats. What I meant to say was scruffies and neats. These are 2 schools of thought in the AI community. When I mention it, I'm rather dismissive of the idea, but Pedro points out that it's actually a useful labeling, so here's the quick definition. A neat is someone that wants to approach AI in a rather rigorous, exacting mathematical way. A neat would want to derive all their ideas from first principles and prove optimality criterion and establish lower bounds and things like that. I'm not sure what it would mean to solve AI, but if a neat solved AI, they'd most likely be able to write it out as a beautiful equation on a chalkboard somewhere. A scruffy, on the other hand, isn't particularly interested in that sort of precision of theory. Perhaps this is because they have more of a hacker's mentality of trying to just take things apart and fiddle with them and inspect the results for something novel. Or more likely, because a scruffy believes that intelligence is too complex a system to be described with the elegance desired by the neat. All right, let's get into it. Oh yeah, and don't forget, stay to the end of the show to hear about the book giveaway. Pedro Domingos is a professor of computer science at the University of Washington and the author of The Master Algorithm. He is a winner of the SIG-KDD Innovation Award and a fellow of the Association for the Advancement of Artificial Intelligence. Pedro received his PhD from the University of California at Irvine and his BS and MS in Electrical Engineering and Computer Science from Instituto Superior Técnico IST in Lisbon. He co-founded the International Machine Learning Society in 2001 and has held visiting positions at Stanford, Carnegie Mellon, and MIT. Pedro's research interests span a wide variety of topics, including scaling machine learning to big data, maximizing word of mouth and social networks, unifying logic and probability, and deep learning. Well, Pedro, to get started, I think most listeners will already be familiar with your book since it has such a strong overlap with the topics we like to get into on Data Skeptic. But for anyone who isn't familiar with the Master Algorithm, can you provide a synopsis?
Sure. The Master Algorithm is an introduction to machine learning for a general audience. So it talks about the impact that machine learning is having today and about the different kinds of machine learning, like deep learning, evolutionary learning, symbolic, and so on. And the quest for the Master Algorithm, which is the unification of those different machine learning paradigms. And then finally talks about the future and some of the things that we can look forward to, maybe be concerned with. So it tries to cover, all the bases in terms of introducing people to machine learning, both in terms of the scientific and technical content and in terms of the implications for business and for society and so on.
Why do we have several paradigms of learning? Why isn't there one clear dominant winner already?
Well, some people would say that theirs is the dominant one. And decade by decade or so, machine learning is about 60 years old. And what's interesting is that the 5 main paradigms all started back in the 50s. And decade by decade, different ones can be on the upswing. Of course, right now it's deep learning, which is learning inspired by the brain. I think the reason there's more than one paradigm in machine learning, first of all, in almost every field, there's more than one paradigm because there's more than one way to go about things. Another reason is that machine learning is not a mature field yet, right? Getting machines to learn is actually a very hard and deep problem, and naturally there will be more than one approach to it. And then finally, and maybe the best reason, is that there are a number of different ideas that if you think about making a learning machine, naturally suggest themselves to you. So one of them is mimicking evolution and natural selection, and that's one paradigm. Another one, which we were just mentioning, is the brain. There's also being inspired by the scientific method and what scientists do, how they discover knowledge. That's another one. Psychology, reasoning by analogy. That's the fourth one. And finally, just doing it based on purely mathematical principles like Bayes' theorem, and that's Bayes learning. So each one of those has a good reason to exist. I and a lot of other people in the field believe that at the end of the day, when the field is mature, these paradigms will be unified. Like, for example, the standard model in physics unifies 3 of the 4 forces, and maybe one day all 4 of them, and hopefully we can reach something similar in machine learning.
I definitely want to get into that unification concept a bit more, But I thought before we do that, it might be instructive to go deeper into one of the tribes as an example. I'll certainly refer people to your book for the complete picture of all the tribes, but as the example, could you perhaps give some details on the tribe of evolutionary computation?
Yeah, sure. Evolutionary computing, it goes by different names, right? It's also known as genetic algorithms and in different versions, genetic programming. This was largely the brainchild of John Holland, who actually was initially interested in connectionist learning back in the 50s, but then he got very interested in evolution. And the idea is that we are going to evolve programs and artifacts, robots, electronic circuits, in the same way that nature evolves plants and animals. We know roughly how evolution works, so we can implement that on the computer. So, there's generations. Within each generation, there's a population of individuals. Again, in this case, they might be programs or they might be robots or something like that. And then what happens is that there's some tasks that we want them to perform, like we want, the robots to play soccer, and we let them do that for a while, and then we see how well they do. And then the ones that do better get a higher fitness score, again, by analogy with evolution. And then the programs or the systems with the highest fitness scores get to reproduce. They literally get to mate, right? So each one of them is represented by a genome, right? In our case, the genome is DNA. But in the case of genetic algorithms, it's usually just a string of bits, right? Because we only need 2 bits for a computer genome, if you will. And then they mate. There's literally a father, genome and the mother genome, and they get crossed over and they produce children. Then they get randomly mutated again to simulate the effect of real mutations. And now you have a new generation. The amazing thing is that if you do this for, let's say, a few thousand generations, even starting from completely random strings, which is what people typically do, after a while, in many cases, you will actually have very high-performing systems. So, for example, the evolutionaries, as this tribe is known, they have a whole slew of patents from the U.S. Patent Office for things like amplifiers and radio receivers and whatnot that are very different from the ones that human engineers design, but in many cases perform better.
Yeah, it's a very interesting milestone in that area that actual patents are issued for things that no person came up with. And a lot is made of that. How significant do you think that is in terms of our culture and society? Are we going to see that path where maybe there'll be a day when algorithmic patents overtake human-issued patents?
Yes, I think this is quite likely. I would say, with the current patent regime, it's probably inevitable. Maybe the patent regime will change, right?
Right.
But if you look at a lot of research labs, right, they basically churn out patent applications, by the thousand, and algorithms can do that very well these days. How useful, most of these patents turn out to be is a different question. What matters is not the millions of patents out there, but the ones that really turn into something important. And I think it's probably fair to say that for the most part, the patents that have been obtained with genetic algorithms have not, changed the world yet. There are many things that are useful, but I think we have yet to see the real breakthroughs. Some things are easy to do, some things are harder. Maybe some of this circuit design, for example, has turned out to be easier than we actually thought it would be. But actually, that's the case with a lot of things in AI, so we'll see.
When I was starting to get into AI, there was this distinction we had of the fuzzies and the neats. And I don't think it's even worth defining because it's an antiquated idea in my opinion. But today we have the 5 tribes that you present in the book, and I have found that this is not only a taxonomy that people from each of the tribes all seem to accept pretty well and say, yes, this labels us and classifies us pretty well, but it's also something that feels very inclusive. When I have said, well, can I think of an algorithm that I know that doesn't fit the paradigm? At best, I think of something that's on the border between 2. With that in mind, have you found that your classification scheme is pretty universal, or are there things that you struggle to fit into the picture?
I think the classification scheme is pretty universal. Having said that, these are the 5 main paradigms. There are others, kind of like smaller paradigms, and there's also orthogonal divisions of the field, right? There's different types of learning. There's supervised learning and supervised learning, reinforcement learning. So there's more than one way to classify things. Fuzzies versus neats is actually an interesting one because I actually think that division continues to exist. And in fact, I think that division exists in almost any field of technology or maybe even any field of science. There are people who just like to put things together and see how they work, and they are satisfied with that. There are people who want to be really formal and principled and really understand what they're doing and have proofs and so on and so forth. And you can see that in the 5 tribes. So, for example, the Bayesians are very much on the neat side, The symbolists also are pretty much on the neat side. The connectionists and the evolutionaries are very much on the fuzzy side, right? Mm-hmm. They just do this learning that's inspired by biology. They don't have as many formal results. Things just work because they work. Nobody knows exactly how. The analogize is an interesting case because you actually have very much people there who are fuzzy, and also people there who are neat, and so it's actually a somewhat looser tribe. So yeah, I think all of these different dimensions make sense. Probably the one that's most useful if you want to understand, some new piece of machine learning that you see is those 5 paradigms, but of course that's by no means the whole story.
I think if we wanted to find a striking example from each camp, we could definitely identify a major technology that has come about through these paradigms. So as helpful as they've become and as advanced as each of them independently is, we still don't call any one of these the master algorithm. What's the difference between each tribe's, best attempt at the master algorithm and the ultimate quest we have?
Yeah, so just to be fair, there are people in these different tribes who do believe that what they have is the master algorithm. So, for example, these days, with deep learning and the connectionists, if you look at what's happening, backpropagation, right, which is their master algorithm, is just acing one problem after another. So many people in that field, including some very respectable people, believe that at the end of the day, we're just going to do everything with backprop, so that is the master algorithm. And some people believe the same thing for genetic algorithms or genetic programming or Bayesian inference or analogy, for example. Douglas Hofstadter, right, the author of Gödel, Escher, Bach, and famous cognitive scientist, he says that everything is just analogy. He has a whole book of 500 pages arguing that. So some people in each of the tribes, maybe the more hardcore members, believe that they do have the master algorithm. However, most people don't, including me, don't believe that that's the case. And the reason is very simple, is that each of these algorithms, in principle, can learn anything from data. So each of these algorithms has a theorem that says if you give it enough data, it can learn any function. By that standard, there are a lot of master algorithms around already. Mm-hmm. But the problem is that in practice, some of these algorithms are good for some things, but not others. So backprop is good for perception, things like visual recognition, speech recognition, and so on. But it's not good for higher-level reasoning and problem solving. Symbolic learning is good for that. So at the end of the day, the true master algorithm is an algorithm that actually can solve well the problems that each of these individual algorithms can solve. At the end of the day, until we have that, we really don't have a complete master algorithm, or at least that's what most of us believe.
Yeah, makes sense. I'm in agreement with you on that. There are various sort of incompleteness results I see in different paradigms, functions that no neural network can learn efficiently is a topic we've covered on the show previously. When we arrive, maybe I should say if we arrive at the master algorithm one day, do you think it'll be some way of synthesizing the existing knowledge, like recognizing when one tribe is good for a problem and having a meta-algorithm that kind of selects which thing to use? Or do we need some new innovation that we haven't yet been creative enough to come up with?
So actually, we already have the format. Something that is very popular in machine learning is meta-learning and model ensembles, right? Mm-hmm. If you look at, IBM Watson or Netflix or a lot of the winners of Kaggle competitions, what they have is this meta-learning thing of combining different models or choosing among them. I'm going to use 100 neural networks and 100 analogy-based algorithms and 100 decision trees and 100 support vector machines and combine them all together. So this already exists and it certainly works. But it isn't really a master algorithm because it's a very shallow combination of these things, right? It's just, treating them as subroutines in a larger routine. For the really hard problems, just choosing one or the other doesn't actually get you there, right? You can't, for example, control a robot that way, because controlling a home robot isn't really just a question of deciding, which one of these or which average of them you should be using. You could say that what you need is just, a deeper unification of them. Again, the standard model in physics is a good analogy. So you don't need fundamentally new ideas so much as you need a fundamental new way to look at these ways of doing learning and seeing how deep down they really are the same. And we've actually made a lot of progress in that direction. So, for example, the work that I've done on things like Markov logic, which initially combined Bayesian and symbolic learning, but now they've also absorbed several of the other things. We've actually made a lot of progress in that direction. So in that sense of a master algorithm, I actually think we're not very far from having it. Whether it will be able to learn efficiently all the things that we wanted to learn is a different question. We will only find out when we try. Now, some people would say that at that point, we've succeeded. My guess, but this is something that I can't prove, is that the there are indeed major new ideas that we need in machine learning that are not present in any of the existing paradigms. So even if we unified them all into one master algorithm, that master algorithm wouldn't still be truly the master algorithm. We would have to, invent some fundamentally new things. And, I have some guesses what they might be. And, and other people have different guesses. And we should let 1,000 flowers bloom at this point.
So I'm not a physicist, but I've read enough armchair physics books that I can pretend a little bit. So I know that the nuclear force, the weak nuclear force, and electromagnetism all unify very well, but gravity is this stickler that just doesn't want to cooperate with its siblings. Can you talk a bit in that context about how the tribes interact today? Are there two that are more closer or more unified? Is there an outlier? How do they all stack up in this regard?
Yeah, certainly. By the way, to pursue the analogy with physics for just a second, there is, something like string theory, which does bring gravity into the picture. It remains to be seen whether it can even be empirically tested. Mm-hmm. There's also things like loop quantum gravity. So at a theoretical level, there certainly are proposals now that unify all the forces. Similarly, in machine learning, there are a lot of people that work across the boundaries, and any two of these paradigms have already been unified in multiple ways. And now we also have approaches that unify 3, 4, maybe even 5, depending on how you look at it. In my book, there's a chapter where, by the end of it, we actually have a unification of all the 5 in theory. Whether that unification will be good experimentally is something that remains to be seen.
How do we reconcile the pursuit of the master algorithm with the no free lunch theorem?
This is a great question. It's actually one of the first questions that people ask me. In fact, the book is like we set out on this quest for the master algorithm, and like the first bump that we immediately run into was like, but this must be impossible because of the no free lunch theorem. Mm-hmm. And the no free lunch theorem says no single algorithm can always be better. And that is a fundamental of machine learning that you can't get around. So how do you reconcile that with the idea of a master algorithm? Actually, the answer is very simple, is that the master algorithm has 2 inputs. One input is data. The other input is pre-existing knowledge or assumptions. So we have, an implementation, open source of Markov logic called Alchemy. And, when you run Alchemy, it literally takes 2 inputs. One is a data set or a set of data sets. And another one is actually some knowledge written down in the form of formulas in first-order logic. When you plug the formulas into the algorithm, into this master algorithm, it becomes different machine learning algorithms. So the same master algorithm can become a Bayesian network, or just naive Bayes, or nearest neighbor, or a decision tree learner, or et cetera, depending on that knowledge that you put in. Without that knowledge, you would be subject to the no free lunch theorem. In a sense, what happens in most machine learning algorithms is that the knowledge that they are implicitly using is implicit. And so people tend to not notice that those assumptions are there, but they are. And as long as those assumptions are hardwired, the no free lunch theorem applies. So what you need to do is actually be able to plug in different assumptions. And then different assumptions will be good at different things, and that is, of course, completely allowed by the no free lunch theorem. I think a good analogy here is the idea of a universal Turing machine. Mm-hmm. The master algorithm is really for induction, what a universal Turing machine is for deduction. You can have Turing machines that do all sorts of different things. In essence, they implement different programs. But then there's also a universal Turing machine that can implement any other Turing machine. And this is really what the master algorithm is for learning.
Are you by chance familiar with Marcus Hutter's work, the idea of universal artificial intelligence?
Yeah, in fact, there's a whole bunch of proposals like that, of different ways to have sort of like this meta-level view of AI, and in some sense have something that is general AI, right? I think the general idea is valid. I think the proposal that, he has more than one proposal, but oversimplifying things, right? It's interesting theoretical, right? But it's very far from being a practical algorithm. Right? The costs are basically unbearable. They can be infinite, depending on how you look at it. So I think it may be a good theoretical starting point, but it's not something that, anybody would go out and use tomorrow to try and do, machine learning on real data.
Yeah, I'd like to emphasize the point you made that when you say costs are infinite, it's not just like, oh, they're so high we don't know how to do it, like what's the cost of putting a civilization on Mars? I don't know how to estimate it. It's really that it's provably uncomputable. So while it's very interesting to study for a lot of regards, there's something quite impractical about it. And I don't mean to be too negative about it. I definitely want to cover that topic more on the show. But with that in mind, it makes me wonder, what if the master algorithm exists, but something about it is quite intractable? It's either inefficient or even finding it is worse than NP. Is there any reason to be very fatalistic about this being a hopeless pursuit?
If the master algorithm is intractable like that, then it isn't the master algorithm, right?
Aha.
Because we have existence proofs. We know that your brain is running the master or a version of the master algorithm right now. So we know that it's possible. An evolution, right, is another version of the master algorithm. Again, the analogy with Turing machines is useful. Turing machines are a universal model of computation, and they were the first one. But every day people publish new ones that are so-called. There will be many versions of a master algorithm that at some level have to be equivalent. But then another good analogy here is microprocessors. A microprocessor, the beauty of it is that it's a universal computing architecture. For anything that you want to do with a computer, there's always an ASIC, right, an application-specific integrated circuit designed specifically for that application that is much more efficient than a microprocessor. So the microprocessor is not really the best way to do anything. The power of it is that it's this universal architecture that by programming with software, it can do an infinite number of things. And as a result, this is what everybody uses, right? Everybody's willing to pay the performance penalty. The master algorithm will be like that too. There will not be any problem for which the master algorithm is absolutely the most efficient solution. You will always get a better solution if you encode something for that problem. But as a general platform to do the learning on, again, by analogy with microprocessors, it can become, the default thing that people use for almost everything.
You had mentioned briefly earlier the Alchemy system. Can you tell me a little bit more about that?
Yeah, so the Alchemy system is an implementation of Markov logic. Markov logic is at heart the unification of Bayesian and symbolic learning. So symbolic learning uses first-order logic. And first-order logic is nice because pretty much everything that we can do in computer science can be expressed easily in first-order logic. So that covers all of that. The big problem with logic is that it doesn't deal with uncertainty, probability, noise, ambiguity, etc., etc. But Bayesian learning does that very well. And there are these representations like Bayesian networks and Markov networks, generally graphical models, that already capture pretty much all the kinds of statistical models that people use, from logistic regression to hidden Markov models to you name it. So we have these two very powerful languages, first-order logic that does pretty much everything in computer science, and graphical models that encompasses pretty much everything in probability and statistics. And so what Markov logic does is it unifies the two. As the name implies, it's a combination of logic with Markov networks. So you write down a set of formulas in first-order logic, and then they have weights. This is what you don't have in logic. A formula has a higher weight if you believe in it more strongly. And then the formulas with their weights, as in a Markov network, they define a probability distribution over all possible states of the world. So this is the basic idea of Markov logic. Alchemy is an implementation of Markov logic where you can easily write down your knowledge, define, different things, input data in different forms, and then do many different kinds of learning. You can just learn the weights, you can learn the formulas, you can actually discover new predicates. There's a full panoply of learning options. And then there's also inference. Inference itself is a hard problem. In first-order logic, people use theorem proving. In graphical models, people use probabilistic inference. And what Alchemy has is the combination of those. And then it also has a lot of useful programming language features like defining macros and connecting to external routines and et cetera, et cetera. So it's like a complete package for you to be able to do machine learning.
Excellent. And I believe that's open source, correct?
Yes, it is open source, yeah.
I'll have a link in the show notes for people who want to check it out. Have there been any interesting use cases you've seen of people who've picked that up, outside of your group and implemented it in some novel way?
So first of all, there's more than one implementation of Markov logic. Ours is Alchemy, but there are many other good ones out there, including ones that, for example, are better for large-scale database-backed things and whatnot. There's, for example, one out of Stanford called Tuffy, and so on. So there's more than one implementation. Markov logic, with or without Alchemy, has been used for many different things at this point, for pretty much across the board, I would say. One, I think, interesting application was in the Kalo project. So the Kalo project was this DARPA project where Siri came out of, right? Siri was an outcome, and then all these virtual assistants indirectly was an outcome of that project. And the goal of that project was to create a virtual assistant, something that these days is something that we all know about, but at that point was a new idea. Is I want the computer to help me with all my daily office tasks, as if it was my own personal secretary. Initially, people were doing that by the way a lot of AI projects happen. Like they were gluing different things together and just became a huge mess, like this wall of complexity. And, we were actually not part of the project initially, but then they came to us saying, like, we need a common, representation language, a common platform, a common set of inference and learning algorithms to make this all make sense, make it all work. And so that's what happened, is that Kalo used Markov logic as, in essence, the central layer between all the different algorithms on one side and the different applications like, visual recognition, natural language on the other. So this is one example.
Yeah, I think that's a really good one. So your book includes a plea that to whomever invents the master algorithm, that they should open source it. Can you talk a little bit about why that's so important?
Well, if someone really discovers the master algorithm, it will be a very, very powerful thing. Too powerful, I think, to be in the hands of any one person or any one company. So that's one aspect. The other aspect is that it will have so many different applications that, again, no single organization will be able to do all of them. And the best way to let all those applications happen is to just open source it, so everybody, every company, every researcher, every individual can go and try it out on whatever they're interested in, and that's how we will make the most progress with it.
In terms of that direction, we obviously see a lot of good work coming out of academia, but also it's been quite profitable to apply machine learning. So we see a lot of private and corporate things taking off. Yet even there, we see different larger companies kind of forming coalitions and things like the OpenAI and organizations like that. Do you think that this long-term will be a collaborative open effort, or does the ability for the master algorithm when we find it, or even the things leading up to it, to generate raw revenue, is it intrinsically opposed to the open source idea, or in some evolutionary way, is that just the natural winning strategy?
I think it remains to be seen. Part of the question is, what will it take to invent the master algorithm? If what it will take is a small number of people that really go very deep and just discover something different from everybody else, from what everybody else already had, right? If what it takes is, a Newton or an Einstein or a Galileo, then I think it is very likely that the master algorithm will come out either of academia or of, some 17-year-old who just came up with that idea, right? That could happen. In fact, it's much easier for that to happen in machine learning and AI than it is in physics or in other more mature sciences. This is one view. Another extreme, which I think is what a lot of people at, these large companies like Google and Facebook and whatnot believe, is this is just a massive engineering problem. What we need is, hundreds of people trying lots of things on very large data sets, with a lot of computing, very fast, and that's how we're going to get there. And if that is the answer, then, of course, the advantage is with these companies that have, these large resources. I don't think anybody knows for sure. Of course, these are just two ends of the spectrum. There are many alternatives in between, and we'll see what happens. I think machine learning actually is a healthy field in the sense that there is a very important industrial component these days, but there's also a healthy academic community. And I actually think that you actually do want both of these things. If you just had one of them, I think our chances of making progress would be smaller. It is true that a lot of the more, again, a lot of the fuzzies, the more applied people have migrated to industry. So maybe academia is a little overweight on the more theoretical types, and industry by nature is more overweight on the applied side. But I think overall, it's actually good to have a community where there are different centers, different kinds of center, different paradigms, different people trying different things.
I recall seeing a TED Talk in which you have this analogy to the evolution of human development versus the evolution of technology within our lifetimes, and how insanely accelerated really things have been in contemporary times. As a result of that, there's become to some degree an alarmism about machine learning and AI. And while I think those conversations are healthy, they also need to be informed with the facts. There is a sentiment by many popular people saying that, we're facing doom here. Data skeptic listeners, I want to tell you about the Mendoza College of Business at the University of Notre Dame. They have a 12-month program in which you can earn a Master's of Science in Business Analytics. The schedule is very compatible with the busy lifestyle of a working professional. On-site courses are conducted on their Michigan Avenue campus in downtown Chicago. Get your Master's of Science in Business Analytics and join an extremely engaged and prestigious alumni group. First step is to visit mendoza.nd.edu/dataskeptic. There you'll learn about their award-winning faculty, get details on this program, and learn how to apply. If your career needs a little kickstart, see if the Mendoza College of Business is right for you. Find out at mendoza.nd.edu. There is a sentiment by many popular people saying that, we're facing doom here.
Most of these people, right, although some of them are pretty well known, are not AI experts, right? If you talk to AI experts, almost universally, they are very skeptical of these doom scenarios. These doom scenarios are more informed by, science fiction movies like Terminator and so on, than they are by the reality of AI. So I think one of our jobs as AI research is actually to communicate this with the public and with decision makers and with people in other fields. I think the mistake that people are making is a very natural one, and in fact is a mistake that the AI pioneers made in the early days, which is to confuse artificial intelligence with human intelligence. Human and animal intelligence is the only example that we know, so it's natural that once we start talking about AI, we would project a lot of human qualities onto it, like free will and consciousness and their own goals and volition and so on and so forth. But emotions and unfortunately Hollywood makes this worse, right? Because their robots and their AIs in the movies are always humans in disguise, right? Because that's how you make the movie interesting and also how you make them easier to understand. But the truth is, AI is very, very different from human intelligence. Intelligence is just the ability to solve hard problems. And the way that you solve those hard problems can be extremely different from the way humans solve hard problems. And in fact, already it is the case, in the future will be the case, that 99% of AI systems out there look nothing like human beings. And even the ones that do, like, for example, home robots, right? A home robot almost inherently has to look like a human being or act like a human being in many ways. But that robot is not going to have a will of its own unless we are so foolish as to endow it with one. It's just going to be an extension of us, right? AI, at the end of the day, is a technological extension of us in the same way that a car is, right? A car lets us run faster, an airplane lets us fly, and AI, extends our brains. But it is an extension of our brains, and I don't think AI is going to turn against us, any more than your hand is suddenly going to slap you.
Yeah, fair point. I'm going to pull one quick quote from the book when you're discussing this very topic, and you say, relax, the chances that AI equipped with the master algorithm will take over the world are zero. I know that you understand Bayesian statistics very well, so if you had said the chances are epsilon, I would have moved past it very quickly, but you chose to say that there's zero. Can you elaborate on what gives you such a confidence about it?
Yeah, I mean, just to be, clear, right? If you read, the couple of paragraphs after that, I do bring up the caveats, right?
Yep.
They are zero unless we are so foolish as to deliberately create an AI that wants to take over the world, et cetera, et cetera. And for that, we need certain safeguards, like what William Gibson called the Turing police, right? Which is AI police, chasing the AI, AI cops chasing the AI robbers, right? It's not that you shouldn't have cars or freeways, it's that the police also need to have cars, not just the robbers. If you want to be precise about it, the chances are epsilon, they are not zero. But, a book is natural language, and in natural language, you don't say epsilon, you say zero, right?
Yep.
It's so small that, for our purposes, you can think of it as zero. And again, you have to take the context of where I say that. It's an AI that is based on the master algorithm. And the master algorithm is an algorithm that, like all of these algorithms, has these three components of, representation, optimization, and evaluation. And the optimization goal is defined by us, right? And I think, at least in the master algorithm, as I describe it, in the book right before that, it is guided by this optimization goal that is defined by us. And as long as that's the case, any AI that starts to diverge from the goals that we'll give it, that will immediately and automatically be discarded. So in that narrow sense, the chances really are zero, right? Unless there was, or maybe epsilon, because there might be some weird electromagnetic storm that causes the right, it's like saying, well, the second law allows a book to fly, into the air, right? It's not impossible.
Sure.
It's just like so vanishingly unlikely that you really shouldn't, spend much time worrying about it.
Yeah, I think that's a great analogy. While we're on the subject of the instructions we give and all the caveats, naturally, AI will be what humans make of it to a large extent. There has been a significant amount of discussion in the community about coming up with bans on AI implementations in warfare and things like that. And I don't know that I totally have my own opinion made up about it, but I think this is an important topic, and I'm leaning towards saying, we shouldn't have AI in war, that it could be a very dangerous or problematic thing. I don't know. I think it's an open discussion, but I came across something striking in your book where you'd said, well, instead of outlawing robotic soldiers, maybe we should just outlaw human soldiers and let a battlefield of robots that, it's just inexpensive if they all get broken down. Do you think this is a real-world way in which we might resolve conflict in the future?
Well, I think, this idea of outlawing humans in combat, I think it would be nice, right? It's obviously a long-term idea for a couple of reasons. One is that the robots aren't there, in order to do that. Maybe they will one day. And also, I think, we as societies aren't actually ready to do that. But to answer your question more directly, I think this notion of banning intelligent weapons is well-intentioned, but it's actually quite misguided. And there are actually several reasons it's misguided. And I know very well the people who've been pushing this, at least on the scientific side. Mm-hmm. And what motivates them is an analogy, more than anything else. It's an analogy with chemical and biological and nuclear weapons. We banned them with the Geneva Conventions. We should ban intelligent weapons as well. But this is actually a very false analogy. The reason we ban those weapons is that they kill indiscriminately, right? They are weapons of mass destruction. The whole point of intelligent weapons is that they are less indiscriminate. An intelligent weapon can save lives. So actually, I think one of the main reasons we shouldn't ban intelligent weapons is that people will die if we don't have intelligent weapons that wouldn't die otherwise. And I can give you a very concrete example of this. If you compare the two Iraq wars, right, both of them, there was a lot of bombing of Baghdad. The first Iraq war, the bombing was not that different from World War II bombing, right? Things got, bombed all over the place. A lot of people died. It was terrible. A lot of civilians, right? A lot of innocent bystanders died. By the time of the Second Iraq War, they had fitted these laser guiding systems on the bombs that, the bomb costs, $1 million, and the laser guided system costs, $50,000. And with that, you can actually the bomber can aim the bomb at a particular building and the bomb will go there. And what happened with that was that they destroyed all the military facilities very quickly. And the civilians in Baghdad were just going about their lives because they quickly realized that they were actually not, at danger. And, there were a couple of instances where a bomb went astray and maybe, 30 people died, which, of course, is a tragedy, but it's very different from thousands of people dying.
Yeah.
And now when you think about the battlefield, right, and soldiers on the battlefield, humans, they get emotional, they have fear, they have vengeance, they have anger, they just make mistakes because they're tired and the fog of war. And as a result, more innocent people will die, as opposed to with, automated systems that could actually potentially do a better job. If I'm ever in a battle zone and there's a drone pointing at me with a gun, the question for me isn't whether the drone should be controlled by a human or by a machine. Is like, I want the drone to make the right decision. So if the right decision is to be more likely to be made by an automated, by an intelligent system than by a human, that's what I want. So I think at the end of the day, there are many reasons. And the thing is, like, for some things, maybe intelligent weapons will be bad. For other things, they will be good. If we ban them outright, we prevent the good ones along with the bad ones. The other side of this is that a ban on intelligent weapons is basically unenforceable. Even if such a convention was actually adopted, you cannot possibly prevent the development of intelligent weapons. Let's do a simple analogy with humans. Any factory worker or farmer can be turned into a soldier by putting a rifle in their hands, right? This is what armies have done through all history. And the same thing is true with a home robot. You take a home robot, you put a gun in its hands, and now it's a soldier. So there's no way that you can develop AI for civilian purposes that cannot be immediately turned around for military purposes. So I think the idea of a ban on intelligent weapons is both, I think, a bad idea in principle and something that is actually not workable in practice.
From time to time, a new idea emerges, and there's uncertainty around it. For a time, maybe people thought Dungeons and Dragons was corrupting minds, and then it was violent video games, and maybe, certain music needed to be regulated. And it seems that all of those cases were needless alarmism. We see today where people are concerned about implementations of machine learning and how it's affecting our everyday lives. We're now in the midst of a discussion about the way our election was conducted. And I'll point out that your book, prior to the most recent election, called out that more and more machine learning was going to affect elections. Are we at a point in history where people are just starting, the general culture is starting to understand what machine learning is, or will the constant advancements of machine learning always make these uncertainties there for us?
Yeah, so I think your list of historical analogies is right on the mark. I think pretty much every time a major new technology develops, there are these fears that run through society. Like nobody will want trains because they will be too scary. Nobody will want cars because nobody can move more than 10 miles an hour without getting confused. Like cameras are bad because they will destroy privacy. Like we're worrying a lot about privacy now, but people say like anybody can go to the beach and take pictures of people with cameras. This will be like the destruction of society. And, the examples are pretty much endless. Television, right, was going to completely corrupt everybody's minds. And
right.
maybe in part it did, right? But in part it didn't. So I think often what happens is that the older generation just judges the new technology by the world that they're used to. And as a result, they misjudge it. And then the new generation actually figures out a way with working with the technology and of, getting the good out of it, and less of the bad. And I think pretty much the same thing is going to happen with machine learning and AI, and in fact is already happening. I think a lot of these fears that people have about machine learning and all the different ways it could be bad, I can see where they would come about, but I think that at the end of the day, a lot of them are misguided fears, right? Every technology has a lot of potential for good and a lot of potential for bad, right? And the more powerful it is, the more that's the case, and AI is certainly a good example. But I think we as human beings, right, we will predominantly put it to good uses and not to bad uses. So it's not like we shouldn't worry, right? Because if we get, too, lackadaisical, then then bad things can happen. But I do think that a lot of the discourse that you see around AI today is basically, worries that are really not very well founded.
Yeah, I'm of a similar mind, and I always appreciate when I find people like you who understand the material and choose to share it with the wider audience through the book, The Master Algorithm, and your talks and other things. So to wind up, maybe I'll ask you a bit of an unfair question, because we know how difficult predicting the future can be. But when it comes to the master algorithm, is this a sort of pursuit that we'll see in our lifetimes, or do you think this is a more longer-term incremental achievement that one day humanity will achieve?
That's a great question, and it's very hard to predict because the progress of science isn't linear. Right? We often have these periods of stagnation followed by periods of rapid progress. We are certainly in a period of rapid progress in machine learning right now, and it's very exciting. But we don't know where this is going to plateau and then how long it will take for the next burst to happen. Mm-hmm. With respect to the master algorithm in particular, it could be that somebody actually has already invented the master algorithm. We just don't know yet. I think it's unlikely, but it actually could be. It could also be, and many respectable people believe that it's not going to happen. At the end of the day, there will never be a master algorithm. It will always be, again, I think the scruffies tend to more believe that there is no master algorithm, and the neats tend to believe that there is. So maybe at the end of the day, it's just going to be, you're going to have to engineer a bunch of hacks, and intelligence is just more and more hacks. So between those two extremes, what I would say is that I think a decade from now, we will have something that looks a lot more like a master algorithm than what we have today. Also because there's now so much at stake economically that these companies like Google, Facebook, Amazon, et cetera, they want to develop these things in order to power their virtual assistants and the self-driving cars and whatnot. So I think we are going to get, the progress is certainly faster right now. Are we going to find the master algorithm in the foreseeable future? I think it'll happen. If I had to guess, I would say it probably will happen in our lifetimes, but, the error bars are very large. Mm-hmm. The other thing to realize is that even if we had the master algorithm today, right, if I had the master algorithm code sitting on my computer right now, between having the algorithm and the full panoply of its applications and implications playing out, it would still take decades, right? So it's going to be a decades-long process, even in the best case.
Well, Pedro, I want to thank you once again for coming on and sharing your thoughts and ideas about AI and where we're headed. Once again, I'll direct people to check out your book, The Master Algorithm, How the Quest for the Ultimate Learning Machine Will Remake Our World. I know it's on Amazon firsthand and any other local booksellers you want to find it at as well. So thanks again for coming on.
Thanks for having me. This was great.
Okay, listeners, let's talk about how you can win a free copy of The Master Algorithm by today's guest, Pedro Domingos. We're doing a little experiment here at Data Skeptic HQ. We need you to help us build our training data set. We're asking listeners to send us their resume. If you're a person deeply concerned about privacy, that's fine. Switch out whatever information you consider private, like your name and email, with some anonymous entry. That's fine. But we'd like your real data in terms of education, experience, and so on. If you're willing to share that, visit dataskeptic.com/MA. That's MA as in Master Algorithm. Just PDFs, please. We're trying to make this all work out very nicely in an automated fashion. We may add LinkedIn Connect in the future, PDFs for now. Everyone who submits their resume is going to get access to a report of exploratory data analysis we do. We're planning some interesting stuff, like telling you how people from your university differ from people at other universities in their career paths. That all depends on our sample size, of course. So please help us out here and send your resume. We've got some other fun things planned that you can opt out of if you don't like them, and we'll be sending those along the way as well. Most importantly, if you submit your resume by the end of March 2018, you'll be entered into our drawing. We'll pick 2 winners at random and send them a copy of the master algorithm. Now everybody, this isn't like the lottery. The sample size of our population is going to give you a non-trivial chance of winning. So if you're listening to Data Skeptic, then you must be interested in AI. And if you're interested in AI, you should be thinking about this in terms of what rational decision you can make. How many entries do you think I'll get? I don't know, 100, 500? Let's say 500. That gives you a 0.2% chance of winning. The book retails for $18.99, so your expected reward here is 3.798 cents. Admittedly, that may not be very much, but for the negligible effort of visiting dataskeptic.com/MA and uploading, not to mention the benefit you get of helping us out in our analysis and those reports you'll get later, well, you'd be irrational not to participate. Anyway, that's dataskeptic.com/MA. While you're there, get on our mailing list, because Monday I'm announcing something kind of cool that's going to change at the website.
Data Skeptic is a listener-supported program. To support the show, visit dataskeptic.com and click on the membership tab.